Hi guys, and welcome to another session. In this video we're going to be looking at the topic of regression. Now, regression is one of the most fundamental ideas in statistics and data science. It's really widely used. It sort of makes up the basis of all sorts of more sophisticated techniques that you'll come on to learn at some point. So understanding linear regression is really important, and that's what we're going to be looking at today. So what is the idea behind regression or linear regression? The idea is basically this: we want to predict some number, some quantity, some variable based on some past observations. So this could be anything. This could be saying something like, I want to predict what is the temperature likely to be next year on July the 20th. We can look at some past data, we can kind of fit some sort of trend, there's going to be some sort of oscillation throughout the year, and we're going to have some idea of what the temperature is likely to be on that date. So that's the basic idea. For this first example here that we're going to look at, we're taking a situation where a car dealership wants to understand the relationship between the number of salespeople that they hire and the number of cars that they sell in any given month. So you can see here that in March they hire 30 salespeople and sell 607 cars. In April they hire 10 salespeople and sell 91 cars, etc., etc. We have some more data, and then they want to know if in August, if they hire 45 salespeople, how many cars are they likely to sell? So that's one example of where you might want to use some kind of regression. So we're using past data and we want to fit some kind of variable in the future. Another example here, slightly more complicated, is we've got a corn farmer that wants to understand the effect that different levels of nutrients in her fertilizer has on her crop yields. So she sets up an experiment where she separates out 5 different fields and puts in 5 different sort of ratios of these base nutrients that she's putting into her fertilizer, so nitrogen, potassium and phosphorus in different kind of levels. And then she measures the crop yield in tons per acre on each one of these fields. And then she might say, okay, well, if I adjust it, if I get a new balance of fertilizers that I haven't used here before, so here it says if I mix it in a 30-30-40 ratio, what crop yield can I expect to get on that new field? So that's another type of thing that we might be able to answer with linear regression. So both of these examples involve predicting some number, which we often call the dependent variable, from one or more other numbers, which we call the independent variables. And basically the most simple kind of model that we can build for this is the linear model. And in this model we approximate our outputs, our independent variables, as a linear function of our input variables. So we'll come on to see exactly what that means, but to just describe it in terms of maths first, we have something like this. We have the number of cars sold, so in the car salesperson example, the number of cars sold, we're going to predict that is a function of the number of salespeople that we hire, and that function is going to be a constant, C, plus a gradient, M, multiplied by the number of salespeople that we hire. So in this case, we are looking to find the variables C and M that best fit that data. So that may or may not make sense. Hopefully it will do in a minute. But first of all, let's just look at this data that we've got. So we're going to run some imports here. So here we're just importing NumPy as NP. We're importing matplotlib.pyplot as PLT. This here, you don't need to worry about. This is some scripts that I've written that are in a different folder that we're going to use in this. So we're just importing some other bits of code that I've written here. And here we're just setting some NumPy print options so that we get pretty arrays out. And once again, we are using this %matplotlib notebook function to give us interactive notebooks. So we are going to plot this. So the data that we've collected, we've got the number of salespeople hired on each month. So in March, we've got 30, in April, we've got 10, etc., etc. And the number of sales that we make, the number of cars that we sell in that month, here we go, 607, 91, etc. And we're wrapping this in a NumPy array. So you've seen NumPy arrays before. They basically allow us to handle large amounts of numerical data more efficiently. So we've got these 2 NumPy arrays. In fact, let's just take a look at those just so we know what we're dealing with. So we're going to run that in there. And now I'm just going to have a look at that. So number of salespeople, cool, that's an array there, 30, 10, 50, 35, 20, and total sales there. Cool, so those two things exist. I'm just going to delete those cells now. And we're going to run this. So we are just plotting here, we're going to scatter plot the data that we've got. So we're doing plt.scatter, our x variable, the number of salespeople, and our y variable, the total sales. Okay, so this is the kind of graph that we've got. You can basically see instantly from this that the higher the number of salespeople that we hire, the higher the expected number of cars that we're going to sell. Some kind of relationship going on here. We haven't got very many data points, so it's difficult to say exactly what the nature of this relationship is. Because we've got a small sample size, maybe just the random fluctuations have given us the appearance of a relationship, but it doesn't exist. So it's difficult to say, or it is difficult to say if there's a more complicated relationship than just a straight line. But with this small amount of data, I think it's reasonable to say that a straight line is, not a bad idea for a starting point for a model here. Okay, so what is a straight line mathematically? A straight line, you may have seen before, can be described by an equation such as this here. So we've got y equals mx plus c. So y, runs along the vertical axis, x runs along the horizontal axis, and for any input x that we care to give, if we already have a value of m and c, then we can get the associated y value with that x. So if say m is 2 and c is 1, if I plug in x is 2, then we'll have 2 times 2 plus 1 is 5, so y would be 5 in that case. And then let's say x is 3, we'd have 2 times 3 plus 1, which is 7, so y would be 7 in that case. So for any value of x, it doesn't have to be an integer, it can be negative, it can be whatever, but we'll always have an associated value of y with that. And if we plot that on a graph, we'll always get a straight line. So these things, m and c, what do they actually do in this equation? Well, m is often referred to as the gradient, and that will basically determine the slope of the line. So if m is really, really large, then for some small change in x, y is going to change a lot because we're multiplying it by a big number. So as say x goes from 1 to 2, y will jump up by a larger amount if m is larger. So you can kind of see here, in this kind of blue line here, we've got a small positive gradient. In this orange line here, we've got a large positive gradient. For these two here, for the green one, we've got actually a small negative gradient. So that means as x increases, y decreases. Whereas over here, we were having as x increases, y also increases. So this is actually a negative gradient. And same here for the red line, that's going to be a large negative gradient because it's a steep negative line. And the effect of the c value is just to kind of shift that line up or down. So c, if you think about it, if you look at this equation, when x is 0, then whatever m is, that will be 0. So you can think of c as being the number which y is when x is 0. So if we look down to this graph here, we've got our x along this axis and our y along this axis. When x is 0, so we've got here the blue line, this is when c equals -3, so -2, -3. And here c is 0, here c is 3. So c can just be seen as sort of shifting this graph up and down, whereas m is affecting the actual slope of it. So our task, basically, if we want to fit a line to this data, then we've got to find the best possible value of m, we've got to find the best possible value of c. So I'm just going to run this graph here. So what have we got here? This is our data again. This is our salespeople data. And in this case, we're going to try and fit some kind of line to it. Right? So I said for any value of c and for any value of m, we get a line out. And our task is to find the best value of c and the best value of m. So in this graph, we can just kind of change those. So this makes c go up and down. This makes m go up. Take c back down a bit. Maybe adjust m there. So I would say for me, that's not a bad fit. That could be our line. That could be the line that kind of predicts the total number of cars that we'd sell for any number of salespeople. So, once we've got our line, once we fit it to our data, we could now say, okay, well, if I hire 45 salespeople up here, I just need to go up to this line and when x is 45, y is going to be about 830. So that's what we'd expect. So when you run this notebook, you can have a play around with that C and M and just make sure that you understand what those two things are doing. Okay, so now we want to ask the question, all right, well, that's all well and good, but we don't, every time we get a new data set, we don't want to have to play around with an M and C. We want to be able to extract these values automatically. So when we start thinking about this, we have to start thinking about, well, how do we quantify how good or bad a certain value of C or M is for our data set? And there might in general be different ways of deciding how good or bad those values are. But one very commonly used way is to look at something called the total squared error. Okay, and this is quite an important concept. You'll see it all over the place in data science. So it's worth understanding now how this works. And the idea is basically this, okay? So our data is made up of pairs, right? We've got an x1 or y1, an x2 or y2, x3, y3, etc. And we can use so if we have a value of m and c, if we've decided on a value of m and c, so let's say I'm going to guess that m is 2 and c is 1. Using that m and c, we could compare what the prediction at a certain value of x is and what the actual observed value at that point is. Now, in this example, actually, what we've got here is we've discarded the c. So we've said, okay, actually, in this model, we're going to say C is going to be 0, which is kind of equivalent to saying if we hire no salespeople, we sell no cars. Now, that could make sense in our context, or it might not make sense if we've got like an online business as well. Maybe that doesn't make sense. But let's say that in this example, we are just the only cars we sell come via salespeople. So in that case, it's not a bad approximation to say, well, when x is 0, i.e. when our number of salespeople is 0, y must be 0. Therefore, c has to be 0 as well. So we're just going to take the approximation where y equals mx. So in that case, for a certain value, x1, so this would be x1 here, is this point here. So x1 is 10, and y1 is whatever it was. Well, actually, maybe that's not true. If we look back to our original thing here, so x1 is going to be 30 and y1 is going to be 607, x2 is going to be 10, y2 is going to be 91, and so on. Then we have two things, right? We have our real observed value of y, the amount of money we made, and we also have our prediction for a given m at that value of x. And these two things are in general not going to be the same. Okay, so here, in this case, at this point, our real measured value of y was 190, but our predicted value of y was about 300 or so. So there's some discrepancy there. There's a difference between the actual height of our measured thing and the height of our prediction at that same point. So that's really what we're quantifying here. So we're saying y1 minus m times x1, that difference, and we're taking that across all of our data points. So we're summing up all of those differences, and also importantly, what we're doing is squaring them, right? So you know what happens when you square a number? You square 5, you get 25. You square 6, you get 36. But importantly, if you square minus 5, you also get 25, right? So a minus times a minus is a plus. So that basically helps us because it means that, well, if our prediction is larger than our observation, this whole thing here is going to be negative. And we're really interested in just the kind of total difference that we have between our predictions and our observations. So we don't really care if it's positive or negative. So we're going to square it, and that way just bigger differences contribute to this error more than smaller differences, regardless as to whether they're positive or negative. So we're going to build up this idea of goodness of fit or badness of fit, which is going to be our total error, which is just going to be that difference squared plus that difference squared plus that difference squared plus that difference squared plus that difference squared. If we had more data points, this would keep going. We're just going to take every single one of our data points and we're going to square the difference between our observation and our prediction. Now, one way that mathematicians would typically write this is using summation notation. Now, all that this thing is saying here is we're saying we're going to take yi minus mxi squared, where I runs from 1 to n, and we're going to add them all up. So this thing here is just saying exactly what this is saying here, where n is 5, because there's 5 data points. But this is more general, right? Because if we had 1,000 data points, this would still be valid. So that's all that's doing there. It's just a quicker way of writing it. And we can think of this total error as being a function of m, right? Because as we change m, our total error is going to change. So at this point, it's probably worth clarifying. There's a few different meanings of the word function that we're using here. Okay, so we have Python functions. We have functions that we use in code, which is the thing you've seen before, where we go something like, def my function of x return x squared, say. So that's a Python function. It's a thing that takes in arguments and returns an output. Then we also have the concept of a mathematical function, right? So a mathematical function is something like, f of x equals x squared. That's how we normally write a mathematical function, something like that. There's some overlap. So sometimes we will represent a mathematical function using a Python function or something like that. But really, they're all kind of related, right? They're all talking about an input and an output. And in this case, what we're saying here is we're saying the error, which is this whole thing here that we can add up given our data set, is going to be a function of m, right? So as we change m, our total error changes. So we can describe this thing as being a function of m, the gradient. So our goal is basically to find the value of m that minimizes this total error, right? So once we've got the value of m that basically minimizes all the distances between our observations and our predictions, then we're going to say, okay, that's probably our best bet. So that concept is explored here in graph 2. So you can see here we've got 2 plots. Up in this top plot, we've got our original data scattered, our original data points here, and we've got a line. And then we've also got these red things here represent the difference between our observation and our prediction, right? And like before, we've got this little slider here where we can change m. So you can see as we're changing m, those red lines are shifting. And then down at the bottom here, what we've got is the total error as a function of m, right? So along this axis, we've got m. So you can see as we're sliding this, that little orange ball is moving to represent that the m is changing. And you can see that the total error associated with that m is changing, right? So this graph down here is a representation of this, right? So as m changes, our error changes. And the idea is that we want to select the value of m that gets us right to the bottom of this curve. So I'll see if I can get it perfectly to the bottom, something like, like that. And you can see up here, but that's a pretty good fit, right? That's basically going to minimize all of the differences between our observation and our prediction. Okay, cool. So we're getting towards an answer. We now know that the best value of our parameter m is going to be when it minimizes the total error. So how do we actually extract that information, right? And to talk about this, we're going to have to discuss derivatives, okay? So you can see, I mean, it's clear visually where the best point on this graph is, right? It's where we have the lowest point. It's going to be right around here. But how do we describe that mathematically? Well, the best point is basically going to be where this graph becomes flat, right? So, it's not flat here, it's not flat here. When we get right to the bottom, it's actually basically flat, okay? And the way that we talk about kind of slopes is by using this idea of derivatives, or gradients. It's essentially the same thing. Gradients and derivatives are the exact same concept. So I'm just going to run this graph here and take a look at what we've got. So not only do lines have a gradient, but also curves have a gradient at one specific place, okay? So for a line, the gradient is the same everywhere, no matter where you measure it. If you kind of divide the amount that the graph, or the line goes up by the amount that you've stepped along in the x direction, you're always going to get the same value no matter where you do that on your line. If you do that on a curve, however, the sort of slope of that curve is going to be different for different places, right? So you can see here that we've got this kind of line running tangent to our curve, which means basically it's just kind of if you try and lie a sort of stick or a plank flat onto your curve, where is it going to fall? And you can see that there are the gradient of the curve at that point is going to be the gradient of this line, right? So you can see that there it starts off, if you look at the gradient sort of reading up here, we start off with quite a steep or a high gradient, and then it sort of gradually shrinks and shrinks and shrinks until we get to this top point here, where we basically get a gradient of 0 at some point. I can't quite get it exactly, but yeah, there's a point here at which the gradient is, that's really annoying. Have I got it? Okay, that's your challenge. That's to try and get it to make it a perfectly 0 gradient at that point. Yeah, so you can run that along, and again, down here, we've got a gradient of 0 somewhere, and then it goes up steep again. And here it's negative, right? Because it's sloping downwards. So we go sloping upwards, positive, 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 0, sloping downwards, negative, 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 0, and then back to positive, sloping up again. So the idea is we want to find the point on our error graph where the gradient is 0. So that's just basically a bit of a kind of mathematical aside, and if you want to dig deeper into the maths of that, there's plenty of resources online. But that's basically the idea. So we solve this, we find the best value of m and c by essentially finding the point at which the gradient of our error function with respect to our input parameters is 0. Okay, so we're going to now go back to the 2-parameter case. So now we're going to stop assuming that c is 0. So maybe we run an online business, and when we hire no salespeople, we also do sell some second-hand cars. So in that case, when the total number of salespeople is 0, we would expect that the total number of cars we sell is not 0. So now our total error, instead of just being yi, our observation, subtract mxi, it's yi observation subtract mxi and c. Right, so now our prediction for any given input point x is no longer just mxi, it's mxi plus c. So if this is our prediction, then we need to subtract this whole thing off our observation. So our observation is yi, and we're subtracting our prediction, c plus mxi, and we're squaring that, and we're adding that up across all our data points. So this little sub-notation here is going to run from 1 to n, which is 5 points in our case. And we're going to add all of that up. So now our total error is not just a function of m, but it's also a function of c. So at this point, the visualization starts to get a bit more difficult, but hopefully with this graph here, you'll be able to get some intuition for it. So what's going on here, right? So here we have two things to vary. So we can vary c, which, as you know, will shift the line up and down. And we also have this thing here, m, which is going to shift the gradient of the line. And now, what's going on in this bottom plot is slightly more complex. But the idea is this, right? The colour of this plot here represents our error. And the point of this little dot here is a value of m and a value of c. So you can see as I'm varying this c, that point on the bottom plot is just going up and down. And as I'm varying m, it's going across. And that means for any given value of m and c, the color of this bottom graph at that point is going to represent the error in some way. So these light colors up here are going to represent a high error, and these deep blue colors down here are going to represent a low error. So the best value of C and M is going to be where this graph reaches its lowest point. So it's going to be somewhere about here, roughly. So it's slightly difficult to tell exactly where the best point is, but if we go up and look at this first graph, you can see that at that point, our error is pretty well minimized. We don't see too much red here. So that line is going to fit the data pretty well. Okay. And just to reiterate, I mean, when we actually would solve this, again, we would be using methods of gradients. So this function here, so that total error as a function of M and C, will also have some flat bit in it. So you could think of this like being a bowl. Like if you roll a pea into a big like glass bowl, it's gonna sort of end up at the point at the bottom of the bowl where it's completely flat in all directions. So it's flat in the X direction and it's flat in the Y direction. So this right here is kind of like a squished bowl, right? And this deep point here is like the lowest point of the bowl, and this is like the sort of high sides of the bowl. So again, to find the point at which our total error is minimized, we're going to want to find the point at which it's flat in both the M direction and the C direction. Okay, so what if we want to add more independent variables? So in that case, we were just looking at the case where we just said that the cars sold are a function of only the number of salespeople. But what if we want to include, excuse me, we want to include other factors? So in this case, we are proposing that the unemployment rate in the UK is also going to affect the number of cars that we sell. So here we have, for every month, the number of salespeople hired, and also the UK unemployment rate. And then we have the number of cars sold. So we're going to predict that the cars sold is a function of both the salespeople and the unemployment rate. And in general, we could have more of these. We could have an unending list of these. We could, look at something else. We could look at, I don't know, the temperature on that day, or we could look at, or in that month, or we could look at, the Bank of England interest rate, or something else, or, the number of coronavirus cases, or whatever. And the idea is that we can basically form a linear model here, where we say that the Y, the output, the cars sold, is going to be some constant again, plus a gradient times our first variable, plus another gradient times our second variable, plus a third gradient times our third variable, and so on and so on and so on. So in the case here where we're just including the number of salespeople and the unemployment rate, we're going to say the cars sold is going to be a constant, plus another gradient, a gradient times the number of salespeople, plus another gradient times the unemployment rate. So what would that look like on a graph? Well, it would look something like this, right? So along here we've got our here we've got our first independent variable, and here we've got our second independent variable, and for every value x1 and x2 we have a y variable as well. So we could kind of plot that on a 3D graph as a 3D coordinate, right? So we've got the x1 coordinate, the x2 coordinate, and the y coordinate, and we can plot that in like 3D space. And then the task becomes not to find a line that fits this data best, but to find a plane that fits this data best. So you could think of it like holding up a piece of paper, and how best do we kind of orient that in space to minimize the distance to all of these points here. So that would be the idea there. And basically, in this case, we'd have something like our total error is a function of C, M1 and M2. And the way that we calculate that total error is by saying, well, we're going to subtract from the actual Y observation a constant plus, so we're going to subtract off a constant plus M1 X1 or XI and M2 XI, and we're going to sum this over all of our values of I, so all of our values in the data set. and we're going to square it as before. And we can actually generalize this further. So we'll go on to this in more detail later, but this kind of way of thinking about things is easily generalized to all sorts of different things, not just multidimensional, not just straight lines. We can actually generalize it to curves as well. So we'll go into the details of the kind of how you implement that and the maths of that. But you can see here that we're essentially doing the same thing. So we've got some other data. We've got, so now I'm renaming these variables. Rather than going y equals c plus mx, I'm going to go y equals a plus bx plus cx, that's supposed to be squared, plus cx squared plus dx cubed. And the idea is we want to find the values of a, b, c, and d that best fit our data. So here we might want to do something like this. So that will be our best straight line fit maybe, but we could probably do better by introducing some curvature. So I think maybe something like this. So it's difficult to find the exact thing that's best, but you can see that we're sort of getting close, kind of. Maybe it would be something like that. I don't know. That's not too good. But basically, by editing these variables a, b, c, and d, we would be able to find some line, some function that fits this data well. And it's actually really hard to do it by hand. So this is the kind of situation where it becomes absolutely necessary to find kind of solid mathematical techniques for doing this. Okay, so that's the end of this session. That was regression. Come back for the next one where we'll be looking at how to actually implement this and solve these problems in Python.